We're going to go through the steps for the Lewis dot structures for two separate molecules. If you ever get stuck on your homework doing these, replay the video, go over, make sure that you're addressing each of the different steps that we go through in determining the structure. If we start with CF4, the first rule, or the first step in doing the dot structure is to decide which atoms are bonded to each other. Now, as it notes here, most of the time the central atom is listed first. So we're going to put carbon in the middle, and we're going to put the 4 fluorines around the outside. Now, the dot structure ultimately is just going to tell us about how the atoms are connected. It doesn't tell us anything about the geometric arrangement of it. That will come later. So it really doesn't matter where we put those fluorines, but balancing them out on each side is probably what makes the most sense. Step 2, determine the total number of valence electrons for the atoms involved. If you're doing a dot diagram for an ion, make adjustments to the total number of valence electrons you have just determined. We'll deal with ions in class later. For right now, we'll just deal with neutral elements. So our two elements that we have are carbon, and there's one atom of carbon in this molecule. And we have 4 atoms of fluorine. So we need to go to the periodic table to figure out how many electrons we have for each of these. So we identified the carbon and the fluorine in our periodic table. Carbon is right here, it's element number 6. Fluorine is right here, element number 9. And we need to determine the number of valence electrons. So remember, if we look at our periodic table, the carbon family, carbon, silicon, germanium, all those, are going to be their valence shell, their outer shell, will be a 2s2, 2p2. The fluorine family adds 3 more electrons to it. So that would be a 2s2, 2p5. And we know that the fluorine, it's one shy of the noble gas configuration, so it shouldn't be too hard to figure that out. So the carbon would then have 4 valence electrons. Fluorine would have 7. Back over to our structure. So we have 4 valence electrons for the carbon. Each fluorine has 7. So 4 times 7 gives us 28 valence electrons to work with the fluorine. So we have a total of 32 electrons that we can put into our diagram to represent how this would bond together. So we have those 32 electrons to put in place. The ones that we definitely know are going to exist in there, we have to have at least 2 electrons that are going to be involved in the bonding between each atom. So we can go ahead and put those in. So we'll put 2 electrons between the carbon and each of the fluorines to represent the bond that's going to form between those. Step number 4 is to complete the octets of the atoms connected to the central atom by adding pairs of electrons. If you're dealing with hydrogen, remember that hydrogen can only have 2 electrons around it. What we're doing here is we're completing that valence shell. Remember that if we look at the valence shell as being the s's, the s orbitals and the p orbitals, 2 electrons in the 1s orbital, 6 electrons in the 3 p orbitals, gives us a total of 8 electrons that each atom wants to have around it. So that's where we get the expression completing the octets. And this is what I like to call the good host rule. So the central atom is going to make sure that each of the fluorines around it are happy. Okay? And electrons are going to exist in orbitals, so we usually put these up here in pairs. So we've now completed the octets of each of the atoms that are connected to the central atom. So that makes each of the fluorines then happy or stable. The last step is to do a count of the electrons you have in place. If you have any electrons left over from your total number of valence electrons, place these electrons on the central atom in pairs. At this point, if the central atom has fewer electrons than an octet, meaning that it hasn't become quite stable yet, then it may be necessary to consider the possibility of multiple bonds, so double or triple bonds, which would involve, further rearrangement of the electrons. So if we look at the picture we have in place right now, we have 8 electrons around each fluorine. And so the 8 electrons around each fluorine, of course, 2 of those 8 are being shared with the carbon, but the 4 fluorine, so that gives us 32 electrons. So we have actually used up all of our electrons. We look at the carbon, and the carbon indeed does have 8 electrons around it. So what we can do is kind of draw a dotted line around each of the elements, and you can see that each one, and I'll just do one of the fluorines, each one ends up with 8 electrons around it. Now, 2 of them are being shared with another atom, but they still have that impression that they have 8 electrons around them, or a more stable situation. Next, we'll try the same thing with CS2. So again, our first step is to decide which atoms are bonded together. So we'll put the carbon with the sulfurs on either side of it. We're going to determine the total number of valence electrons that we have for our element. So again, we've got to go back to the periodic table. Our first element is carbon. And so for the one atom of carbon, we just checked, and we had 4 valence electrons for the carbon. So let's go back to the periodic table and check out the sulfur. So our sulfur is right here, element number 16. So it's going to be in the 3rd period. So sulfur is going to be a 3s2, and looks like we're 4 into the p's, right? So 3p4. So if we add those two together, 2 s's, 4 p's, we have 6 electrons with the sulfur. So we have 2 sulfur atoms, and each one has 6, so that's going to give us 12 valence electrons to work with there. So we're going to have a total of 16 electrons to work with. We're going to put a pair of electrons in the diagram for each bond. So we want to make sure that the sulfurs are going to stay attached onto the carbon. So we're going to put some electrons or electron density between the atoms of the bond. We're going to want to do our good host rule. So we're going to complete the octets of the atoms that are connected to the central atom. So that makes our sulfurs more stable. And now finally, our last step, we're going to check and see how many electrons we've used up. So we used 16 electrons, which is all we've got. So we don't have any more electrons. Now in this case, we do have a problem here, because the central atom does have fewer electrons in an octet. So the sulfurs are happy and stable, but the carbon isn't. So how are we going to rearrange the electrons so that the carbon gets more electron density, but the sulfur doesn't lose its electron density? Well, we're going to take the electrons from this sulfur, one of the lone pairs, and we're going to put that between the carbon and the sulfur. And we're going to do that for the other one as well. So now if we look at each atom, that sulfur still looks around it and sees 8 electrons, and the carbon will also look around it and see 8 electrons as well. And so by doing this, we actually create a stable situation for both. Not as great a situation as what they might have if they only had to share 1 pair of electrons, but sharing 2 would be fine. You heard me describe these other pairs here as non-bonding pairs. Or sometimes called lone pairs. And then the pairs that are between them that are involved in bonding are bonding pairs of electrons.